Welcome to this course on power quality. So, today we will like to start this topic of active series compensation. So, the outline for today presentation is introduction, state of art on active series compensator, classification of active series compensators, principle of operation of active series compensators, analysis and design of active series compensator, then control of active series compensator because it is an active device, and then we will like to take a case of modeling, simulation and performance of some case strategy of active series compensator, followed by then some numerical example and the summary, and followed by references. So, the very objective of this active series compensator is we will like to discuss first the requirement of it and application, then we will go to the configuration of active series compensator, then we will go for a analysis and design of active series compensator, we will discuss control of active series compensator, and then method of modeling and control of active series compensator. Well, coming to like introduction, typically for voltage based power quality problem in distribution system, what are the voltage based power quality problems, like typically voltage sag, voltage swell, voltage unbalance, voltage flicker, voltage tangents, then voltage notches, voltage fluctuations, voltage distortion, voltage imbalance, and of course, the voltage harmonics, maybe there may not be there. So, these are the some of the voltage based power quality problems in distribution system, like either it is typically we discuss already whether it is natural or it is man made, because of which reason it is coming into practice. So, solution is active series compensator, or we call it DVR, dynamic voltage restorer, or the solid state synchronous series compensator is also called SSC. So, the different is known from different names, like, and they inject the equal and opposite voltage of disturbances in series synchronism with the AC mains to protect and to provide clean regulated voltage waveform across the critical load. Well, coming to this dynamic voltage restorer, these are the typically some photographs of the already existing this typically this STATCOM, and industry pure wave is also manufacturing this DVR, dynamic voltage restorer. This is typical photograph of that, and this is another photograph from dynamic voltage restorer from above industry, and the dynamic voltage restorer, this is another type of photograph how they are installed in practice, where they are located virtually, and then the typically for the industry or for process the typical photograph. So, coming to that on state of art on this DVR or series compensator, active series compensator. Now, it is a mature technology to eliminate the voltage spike, to eliminate voltage sag, to eliminate the voltage swell, to eliminate voltage notches, to eliminate voltage harmonics, to regulate the terminal voltage, to suppress the voltage flicker, and to mitigate the voltage unbalance in 3-phase system. Like, well, development on this of series compensator have been in varying configuration with the advanced control technique, and different solid state devices are used in that, and of course, responsible is improved sensor technology like Hall effect current sensor, voltage sensor, which are now at reasonable cost, but they are very fast and they do not distort the signal also. And another reason for its revolution have been a microelectronics revolution, because this microcontroller and DSP they have become at very low cost, much lower cost, much lower cost, even the cost less than even a single power semiconductor power device like IGBT. And these are the typical photograph. If you look into on left side current sensor, on right side you see the DSP. So, coming to the classification of active series compensators, we classified first on the converter types. So we can use of course in current source converter with the bridge structure, or we can use the voltage source converter bridge structure. That is about converter based classification. The another classification we give like a topology based classification, like half bridge, like a full bridge, the transformer less configuration, and another classification is based on number of phases, like you are going to use it in 2-phase like a single phase supply system, or you are going to use 3-phase supply system, or you are going to use like a 3-phase 4-wire supply system. So, coming to the converter based classification, you can just see the circuit of current source based single phase DVR or series compensator, where very purpose is that we have a supply and we have a source impedance, followed by the series compensator, which is using current source converter, and of course, regulating the voltage across the load and maintaining the sinusoidal voltage across the load, so that load operation is not affected if any power quality problem of voltage is there on the load side, like a sag, swell, other similar problem are there. So, now this current source converter, have a typically you can think about on DC link as energy storage, it needs an inductor, and as a switching device, because in current source converter you require your negative voltage blocking capability and IGBT or transistor family, either MOSFET or IGBT or typically your BJT do not have a negative voltage blocking capability. So, we have to connect a series diode in addition to that to take the voltage reverse voltage block across this. So, when it conducts, it is a loss of both the devices. The losses are increased while in conducting, and the inductor is also costly, bulky and lossy compared to the dielectric capacitor, which is used in voltage source converter. And of course, we have to, this capacitor is also mandatory, because these are the pendulum voltage or pendulum current, and you have to make a current in the transformer winding, which is a continuous current and sinusoidal voltage. So, this capacitor is mandatory for that, and of course, DVR required, sometime transformer does not require transformer. So, current source converter have certainly some of the drawback which I mentioned, more losses, high weight, and typically the bulky structure like. So, the current source converter are considered substantially reliable, but have higher losses and require high value of parallel AC capacitors of this one, and they cannot be used in multi-level or multi-step modes to improve performance in a higher rating, where in voltage source converter you can use multi-level as well as multi-mode type of structure. So, another structure is like a voltage source converter, because here it is shown in brief, because we will discuss many structure of this voltage source converter little later. So, we have a supply and we have a source impedance and we have a critical load. Across this we want to keep the voltage, even this load may not be drawing a good quality current, but we still need the voltage of good quality across the load, regulated voltage. So, this DVR, or you can call it the series comparator, is supposed to inject the voltage in series to compensate any voltage power quality problem at the point of common coupling, like a voltage sag, voltage swell, or voltage notches, spike, surges, notches, all the kind of this is supposed to be compensated by this with power control. So, for this of course, we use, since transformer is used, there is no need of interfacing inductor also, we can adjust the leakage reactance of this transformer. And apart from that, of course, you can see the device here, it is transistor family support very well with the IGBT, with the anti-parallel diode to provide the feedback current and as a free link diode. And on DC link we have a dielectric capacitor, which is very cost effective, as well as it has almost negligible losses and its weight is also quite low. So, in light of these advantage of voltage source converter, voltage source converter have taken the lead for even for this DVR applications like, and this is a typical example of single phase circuit. So, these with, we can call it voltage source based single phase DVR, they are lighter, cheaper and expandable to multi-level or multi-step version, and to enhance the performance with lower switching frequency, it is more popular in UPS based application. Coming to the another classification, like a topology based classification, you can just see here, if we give a more detail, like maybe like a source impedance. So, voltage source converter, as we discussed, that it is better. So, we can use a half bridge, okay, is a critical load, we have to regulate the voltage across this. Whatever the power quality problem of voltage is there, it is supposed to be mitigated by series compensation provided by series voltage here. And in the half bridge, you, of course, you save the two devices, but the drawback of this, the voltage rating here on the DC link have to be double than the full bridge one, and moreover the entire current have to flow through these DC capacitors, and the size of the DC capacitor have to be large also. So, these are the typical drawback, and because of this reason we prefer to use the voltage source converter typically in a bridge configuration. This is bridge configuration here, and we have to maintain again a voltage here, so that pendulum operation is satisfactorily here, and this is supposed to inject the voltage here, in the line to compensate what are the power quality problems. So, that regulated voltage and good quality voltage waveform are applied across the critical load, like, but there are plenty of critical load. So, coming to again the another configuration, especially for 3-phase 4-wire DVR, we have a supply and we have a source impedance. So, we have, and this is the 3-phase critical load, where we want a good quality of voltage with balanced voltage, sinusoidal voltage, regulated voltage. So, if there are any voltage quality problems here, either voltage sag, swell, unbalanced notches, spike, that have to be taken care by the series compensator, we call it the DVR, and this pendulum, along with the transformer, this pendulum inverter is supposed to inject the voltage with the appropriate polarity as well as with the appropriate waveform, I mean with self supporting DC bus, or you may have a, we will discuss those a little later, another classification that you must have good quality voltage here. Well, coming to supply based classification, which we already mentioned it, like it is a single phase, I mean 2 wire DVR with the current source converter, we already discussed it across the load, and this is single phase with the voltage source converter, I mean DVR. And then coming to 3 wire DVR topology, I mean which we classified into different category. Of course, this can go the classification in single phase also. So, first is the rectifier supported, and now question is DC link, how it is supported. So, DC link is supposed to be by rectifier. We can put the rectifier on left side on supply side, or we can put right side of the typically of series compensator, and of course, we can use the 3 single phase VSC or 3 leg VSC or 2 leg VSC in both side of these configuration. So, another how we classified was 3 wire 3 phase 3 wire DVR, that we can have a battery supported for all 3 configuration, like 3 single phase voltage source converter or 3 leg voltage source converter or 2 leg voltage source converter, or we can have a self supported capacitor supported typically of this DVR with the 3 single phase VSC or 3 phase 3 leg VSC or 2 leg VSC. The one very important aspect here is, I mean you can find it in capacitor supported, I mean like as well as rectifier supported, you have some limitations, we will talk about those limitations a little later. So, this is the first case of 3 leg voltage source converter, where the rectifier is put on the left side of this DVR, and we are supporting this with the help of extra energy from typically from this rectifier to maintain the DC link voltage. Of course, there is no problem, you can put simple rectifier with the proper appropriate voltage here, I mean for maintaining this, but the transformer size and the voltage rating have to be accordingly chosen. The major difficulty of course, in this case is that you can feed the active power, you cannot take the active power back here. So, those are the limitations. Another is this rectifier, of course, we do not, I mean if you are taking a power from here, then certainly this it will draw distorted current, that distorted current flows into the line. So, that is certainly the difficulty here, but this is capable of by you can of course use the reactive power for compensation, but small active power you can take in only unidirectional, but it provides the. So, another one typically is with the 2 leg, that was with the 3 leg with the rectifier supported, and this is really 3 single phase with rectifier supported. So, you have a rectifier supported with 3 leg independent control for all 3 phase for voltage injection, because you may require the separate voltage injection for all 3 lines separately, because the unequal voltage or unbalanced voltage may be there. Here we like to balance the voltage across 3 phase critical load. And then this is that if you put the rectifier on load side, I mean like you can have a, I mean the rectifier supported in this case. Well, this sometimes some of the topology get even the DC link can be of the load, that we will talk little later in some of the maybe series active filters also. So, it can be the rectifier on the left side with the 3 leg, or it can be with the 2 leg rectifier supported on the right side, or it can be 3 single phases with the rectifier on the typically right side of the DVR, or you can have a battery supported. So, now battery you can connect either DC link directly, or you can connect the battery with the DC-DC. That DC-DC along with the DC-DC converter, it allow the 2 benefit. One is that battery voltage can be at optimum level. The another benefit with this DC-DC converter is that you need to allow the second harmonics to go to the battery to flow into that. So, that benefit you can have with the battery. Of course, you have to afford in size and cost and weight of the battery and maintenance requirement of battery, but the very benefit that you can inject the voltage at any angle now. I mean because you can take the power, you can feed the power. So, you can inject, and of course, reactive power you can generate from the converter. So, you can inject the voltage at different angle, and you can have a very versatile operation of this 3 leg voltage source converter DVR. Similarly, you can have for 2 leg also, which is not much, because I told you the entire third current flows into the capacitor, and this capacitor becomes quite bulky also. Or you can have a 3 single phase one. So, you can have a very independent control, and this power electronics you can design at quite different voltage, low voltage also, and accordingly you can select the battery voltage with DC-DC converter like I mean also. So, this becomes very interesting configuration for practical application, and battery rating need not to be very high if you are not circulating large amount of active power, you are not using for compensation. If you are managing with the compensation with the help of active power, reactive power only, on during dynamics only you need some kind of active power which you can, but the charging of the battery and discharging of the charging of the battery also have to be take place from the same circuit. So, maybe under normal operation I mean, you have to take some active power to charge the battery, and during dynamics you have to take this back, so that under dynamic condition also you are able to regulate the voltage very effectively in this configuration. This is the typically you can call it the capacitor supported, self supported, capacitor supported. So, we take a small amount of active power to support the this voltage across the DC link across the capacitor, as we have done in case of D STATCOM. But you can understand, I mean, the control becomes reasonably involved in this case with capacitor supported one, and of course, you cannot trust to inject the voltage except for very short period. You can take some power, some energy from the capacitor, but not regularly. Again, you have to rebalance, otherwise pendulum control will not be successful. Well, but reactive power injection you can certainly regulate the voltage, and you can maintain even unbalanced voltage also can be injected with this. You can use 2 lag also, but I told you the limitations of 2 lag. The voltage rating increases substantially high, apart from because each have to take a typically kind of phase voltage, and then 3 lag VSC with the capacitor support. So, this is quite versatile and can be designed at low voltage, and you can inject it with the self supporting DC bus of the 3 single phase, typically of DVR or series compensator. Or another is that you can support directly on the battery of the DC link, like best supported we can call it, and along with the capacitor here. So, battery can be charged or can be discharged, because for very short period you can take substantial energy also. During dynamics, because we call it dynamic voltage restorer, it means during dynamics also you might have a voltage typically kind of fluctuation, sag swell, or a tangent phenomena. So, you require some burst of energy for the compensation also, so that these voltage are not affected during sag and swell. So, during swell it had to take energy, and sag it had to feed energy along with the reactive power for the compensation, like also. Well, this is like a capacitor supported, typically example with the proper component value, that you have interfacing inductor, you have ripple filter. Of course, I told you that if you are using leakage reactance, then this capacitor ripple filter goes across the other secondary side, because we cannot put otherwise like on that. So, that is capacitor supported DVR, like So, now coming to very purpose, that how typically you can think about the different cases. Here is the phasor diagram of capacitor supported DVR. So, for voltage sag condition, this is the typically voltage sag. We consider this is the rated voltage, but there have been a sag. So, what you have to do now, you have to inject the voltage, and typically this is the current, original current of the load current with the voltage, and now current will go this way. So, you have to inject the capacitive current, and this is quadrature axis, this is direct axis, and you have to maintain this voltage, which is the rated. Could have been with before sag, this was the voltage, after that this is the voltage, during the sag this is the voltage, and you have to regulate to this the voltage, and that is possible only when you are able to inject the voltage at 90 degree from the current, like because this voltage should be 90 degree, otherwise you will require active power, because it is a capacitor supported, you can have a reactive power, but not the active power. So, that is the reason you have to have the this current should be 90 degree with the voltage injection 90 degree with this, which can behave like a either inductive behavior or capacitive behavior as far as injection of the. So, the second case is like a voltage swell. So, your voltage have increased, ideally voltage should be lower like this, but suddenly voltage have increased more. So, you have to reduce the voltage by again injecting the voltage, but this voltage injection have to be at again exact 90 degree for purpose of your only reactive power injection, not the active power, because active power in capacitor supported will not be there. But of course, for voltage regulation you may require little active power, that have to be accordingly taken care in the phasor diagram also. Or in 3 wire you might have unbalanced sag, this is unbalanced sag, means this is the unbalanced sag here, but for across the load how will regulate, you have to inject the voltage here, you have to inject the voltage here, then the line voltage will be a balanced and regulated voltage. So, this voltage are required to be injected in 2 line only, not necessary typically in case of 3 line, one may be as it is, other 2 line. So, that also give you a concept that the injection can be in 2 line to regulate the typically the voltage in unbalanced voltage conditions, like also there have been some publications corresponding to that, like So, coming to principle of operation of this DVR and dynamic voltage restorer or series compensator, active series compensator, a voltage we injected is inserted such that the load voltage is constant in a magnitude and undistorted, though the supply voltage is not constant and magnitude or may be distorted. So, the very principally we have a source voltage, we have a source impedance, this voltage may not be a regulated voltage, okay. It might be having all the voltage based quality problems, but this voltage will be regulated across the critical load, and we already discussed the critical load, lot of process where even a small sag may cause the process to interrupt or the protection may trip, and by putting this appropriate voltage maybe you can keep the battery also, because you can inject the voltage at different angle even during dynamic conditions. So, you can inject the voltage at appropriate angle with proper control. So, that is virtually you can call it like how typically the DVR work properly, and this is the different conditions how the principle of operation. Why we have considered the battery? Because you will be able to inject the voltage at different case like. So, here you have a different conditions of the load also. So, you can say originally like this is the voltage, okay. You can inject this voltage in phase, okay, which require active and reactive power. You can have a the drop of this voltage in at the perpendicular to the current or in phase with the current. So, in phase will be corresponding to active power, quadrature will be reactive power. So, you have to inject this voltage, or you have to inject this voltage, or you have to inject this voltage or this voltage, which give the regulated voltage or so. So, depends like how you will be able to reduce the rating for a given condition to regulate the voltage across the load. So, there are you have a typically many conditions corresponding to depending upon the the voltage injection at what angle you are going to keep. So, this is like a pre-sag, this is the voltage sag how it has been, and after the sag you have to. So, pre-sag means this was the voltage earlier, and now after the sag this voltage have reduced virtually this, and now you are going to inject for different conditions to regulate the voltage. So, that the voltage across here the load which we call it is all regulated, and these are the injected voltage like VC1, VC2, VC3, or typically like VC1, VC2, VC3 and VC4. So, that the load voltage are regulated like. So, single diagram and phase diagram of DVR voltage injection. So, a pre-sag is the voltage across the critical load period to voltage sag condition. So, during the sag the voltage is reduced to Vs, that is virtually you can call it like a typically this one, it reduced to this one. Earlier it was typically this one, we call it pre-sag, this is the load voltage, and now it is reduced to this, and now we have to see how we will be able to typically during the sag the voltage is reduced to Vs with a phase angle of theta, and now the DVR inject a voltage so that the load voltage magnitude is maintained at the pre-sag condition, and accordingly to the phase angle of the load voltage the injection of voltage can be realized in 4 ways. So, VC1 represents the voltage injected in phase with the supply voltage. The injection of VC2, the load voltage magnitude remains the same, but it leads by Vs by a small angle, and VC3 the load voltage retains the same angle as the pre-sag condition, which may be an optimum angle considering the energy source at DC bus of VSC use DVR, and the VC4 is the condition where the injected voltage is in quadrature with the current, and this case is suitable for capacitor supported DVR, and this injection involved no active power losses in the DVR. So, this is the condition you look into if it is a typically this condition, because this is at 90 degree from the current. So, it needs reactive power only like kind of things like. So, that is the fourth condition. So, the minimum possible rating of the power converter is achieved by VC1 when voltage is injected in phase with the supply voltage, because that is directly algebraic sum of them, does not matter what active and reactive power it needs or so. So, coming to like analysis and design of this DVR, the design of DVR includes the voltage rating of voltage source converter of DVR, current rating of voltage source converter of DVR, an estimation of kVA rating of the voltage source converter of DVR, and the injection transformer rating, then DC bus voltage rating, DC bus capacitance rating, and AC inductor interfacing and ripple filter rating. So, coming to the design of voltage rating of the voltage source converter. So, considering a voltage fluctuations between plus 20% and minus 30% and a 6% voltage underbalance in the PCC voltage for a 3 phase 415 volt 50 hertz 20 kVA kVA load for which we are designing critical load for which we are designing this DVR. So, voltage rating of VSC of DVR depends on maximum voltage to be injected in this condition of critical load. So, maximum voltage sag in the terminal voltage is obtained as your typically load voltage will be 239.6 multiplied 7. So, it comes 167.272 volt, and now this voltage have to be injected at the quadrature with the supply in case of self supporting DC bus, DVR, therefore, injected voltage will be your VSC square minus VL. So, this is you are calculating the DVR voltage. So, this is the supply voltage, this is the load voltage, okay, or we want this voltage across the load, but this has gone to sag. So, this is the voltage at which are injecting quadrature, because we want self supported, means we want only reactive power, the voltage to be injected by reactive. So, this is the rating, voltage rating of DVR considering a unity power factor load for just most simplest case, and the current rating of DVR depends on the load connected to downstream of the DVR, or you can call it current rating of DVR is same as the load current rating. So, we have a 20 kVA load and current can be calculated from this relation root 3 VL/IL, and from this we get the IL equal to 27.82 ampere. So, current rating of DVR will be also the same, and the kVA rating of the DVR will be typically of your 3 times the voltage injected by DVR, and current rating of DVR 3 into 170.1 into 28 point, and this comes 14,280 VA and 14.28 kVA. So, rating of injection transformer, the injection transformer design considering the optimum voltage of the voltage source converter, and kVA rating of the injection transformer is same as that of DVR rating, which is calculated earlier 3 VR DVR by 1000. So, 14.28 kVA, and the typically the turns ratio we can select, because this is the voltage to be injected on line side, and this is the voltage we want on secondary side on which we are putting the inverter. So, voltage rating of secondary or winding or VSC is considered here 50 volt, and now from this we can design the value of capacitor of voltage source converter. So, the DC link voltage, now DC link capacitor voltage is selected based on the following relation, that VDC equal to root 2 into VSC, where VSC is the typically AC voltage is 50 volt and value of VDC will be corresponding to 141, and we can round off this to 150 volt of the DC link on inverter side. Coming to DC link capacitor of this voltage source converter of DVR with the transformer. So, DC link voltage is selected based on the transient energy required during change in the load, and is calculated as half CV half CD in bracket VDC square minus VDC 1, and this is the minimum voltage, this is the nominal voltage, and then the energy have to come certainly from 3 VC IS into delta T. So, delta T is the time for which you require the support required. So, considering the typically delta T 200 microsecond, VDC 150 and 5% reduction in this. So, typical allowed, let us say we allow 5% reduction in DC link voltage to take the energy back during dynamic condition. So, it comes 142.5 volt, and DC link capacitor CD is calculated as from this relation, and it comes 2603.76, and the DC link capacitance round of 3000 microfarad of rating of 200 volt can be selected for DVR also, because during dynamics it can go the voltage during 150 volt, more than 150 volt also. So, coming to the design of interfacing inductor for voltage source converter of DVR. The interfacing inductance is selected based on the current ripple in the current of DVR, and considering the current ripple of 2% with the modulation index 1 and overloading 1 factor of 1.2, the interfacing inductance can be calculated from this relation. Putting the value, it comes like a typically 0.948 millihenry, which can be of course adjusted by leakage reactance of injection transformer also, and hence an interfacing inductor of 1 millihenry and 50 ampere current carrying capacity is selected for the DVR. Coming to design of ripple filter, the ripple filter is designed for eliminating the switching frequency ripple from the injected voltage of series this DVR or series synchronous static compensator. So, ripple filter is a combination of CR and resistance RR connected in series, generally tuned at half the switching frequency FR, and that is half the switching. So, considering 5 kilowatts half the switch, so we can find out typically from this value. So, selecting the resistance of 5 ohm which is easily available, we can get the capacitance value of this, and then we can select the next value. So, coming to RR equal to 5 ohm and CR 10 ohm is selected to design a ripple filter for a switching frequency of 10 kilowatts. Coming to the typically the control of DVR, we already discussed the control in DSTATCOM. So, we can classify the control algorithm on the same basis like time domain control algorithm, like a synchronous reference frame theory, also known DQ theory, unit template technique or PI controller based theory, or instance reactive power theory, also known as PQ theory or alpha beta theory, instance symmetrical component theory, and neural network based theory. We do derive LMS based Adaline algorithm, or single phase PQ theory, single phase DQ theory, enhanced PLL based control algorithm, or adaptive detecting algorithm also known as adaptive interference cancelling theory or any more. So, there are plenty of algorithms are available now in the literature which you can apply for this DVR. Similarly, we have a frequency domain control algorithm also like a Fourier series theory, discrete Fourier transform theory, fast Fourier transform theory, regressive discrete theory, Kalman filter based control algorithm, wavelet transform based, Stockwell transformation based theory and empirical diffusion theory and Hilbert Huang transformation based theory and many more. So, these are frequency based. Of course, they are slow, but people have modified because now processors are available very fast. So, even we can implement these also on this control of this like So, coming to like a DVR control algorithm, the frequency domain algorithms are used for power quality monitoring and number of purpose in the power analyzer, power quality instruments etc. So, some of the frequency domain control algorithms have been used for the control of DVR. However, these algorithms are sluggish and slow because requiring heavy computational burden. Therefore, these algorithm methods are not too much preferred for real time control of DVR as compared to the time domain control algorithms. So, frequency domain control algorithm are used for power quality monitoring and power analyzer and some of the frequency domain used. So, these typically the you can call it the synchronous reference frame theory based control algorithm of DVR with battery supported DVR. So, what I mean if we look into this algorithm, the very purpose of DVR to regulate the voltage across the load. So, here we have a source voltage we are sensing and from PLL of this we are getting either PLL or we can take a template. So, we are getting cos theta sin theta which is required for transformation. I mean both side, I mean we require transformation here, we require transformation here and we require final transformation here. You can understand the transformation is required in 3 times in synchronous reference frame theory. So, we take the source voltage, I mean like you can just see the source voltage, we have a sense load voltage. So, we convert dq and we get the source minus the load voltage. So, this is the typically equivalent to we can call it compensating voltage and we have a from load voltage we can find out like a reference voltage we have okay. From template we can get reference voltage and then from reference we can have a dq component and we can add from load. So, we will get a compensating voltage here and this compensating voltage with the difference of this we can have typically controller here PI controller to regulate this voltage and then after output of this we add this voltage feedback we call feedback. So, we are getting virtually to be injected voltage here in dq and with the transformation back we get the compensating voltage which we have to have a compensating voltage and these are the sense voltage across the VR and we get the gating pulses of DVR. So, this is how we modify this SRFT theory synchronous reference frame theory for control of DVR with battery supported. Why we are considering here battery supported because we can inject the typically the voltage at any angle. We are not considering the angle here because we are not sensing the typically the load current. We are just only sensing the all load voltage and then the source voltage and then even the voltage of the compensator like. So, this is totally on control on voltage based theory like. So, SRF based theory typically I mean the equations for if you look into the amplitude we have to find out the voltage which we like to regulate, we like to calculate the template which we discuss it and from template and reference voltage we can find out the reference load voltage like your template require from load voltage only where it should be typically the same voltage magnitude required and then from this same way from load voltage using this again the path transformation we can find out even the dq voltage of the load also and similarly the load voltage reference also from PCC also converted into dq reference frame. I mean like so both are in dq load as well as the source voltage. So, we can get a now the difference of this dq in compensating one and from we can find out the even a compensating reference voltage also. So, these are actual compensating voltage, these are reference compensated voltage because we have a reference load voltage minus the actual load voltage. So, we can get typically from there and then these voltage error between the reference and actual DVR voltage in dq are regulated using PI controller. I mean these are the typical error in dq and using PI controller we are able to get typically this reference dq. Of course, 0 sequence is not there because of 3 wire, but we get a dq compensating reference voltage from which we can get 3 phase compensating voltage and these we can compare with the sense compensating voltage to get the regulated voltage across the load. So, reference DVR voltage and the sense DVR voltage are used for PWM controller to generate the gating pulses for the voltage source converter of DVR. This is of course typically the again synchronous reference frame theory based control with self supporting DVR. Of course, we discussed already the self supporting DC bus, it means we have to put it, we have to maintain the DC link voltage. Apart from that, the injections will be of voltage preferably at 90 degree, because it should need the reactive power only. So, here of course, with this voltage source converter we have a reference voltage, we have a feedback voltage. As I told you that here also you might have a even some of the ripple, even the second harmonic wave voltage unbalance has to be compensated. So, this low pass filter is required to get DC component. Then we have a PI control. This represents the voltage corresponding to the loss which we have to inject for getting the power from the same circuit. I mean, like you can call it, it will be injected in phase with the current, so that active power is taken. So, similarly from source voltage we transform into typically into ABC to DQ, and from current we are taking now PLL. That is also more important there, so that current is taken care into that we inject the some voltage, most of the voltage in quadrature, but a small voltage is injected for power, real power is only at the phase. So, we get VSD by SQ, and of course, this might also because have a AC component also because of distortion. So, we use low pass filter, get DC component, and V loss we subtract the loss from here. So, we get injected typically corresponding to the this as a active component of the voltage, and similarly for reactive component we add from this voltage regulator. So, we have a load voltage, we have a reference amplitude of load voltage, and we have a estimated load voltage, we put PI controller. So, we get corresponding to the voltage to be kind of injected by this series compensator. We add the load, and then we get the total voltage across the load. So, we get two component of load voltage, and then we take a PLL. So, we get the load voltage, I mean 3 phase instance load voltage, which are sinusoidal, balance and regulated voltage. We sense the actual voltage, load voltage, and we calculate that. So, this is indirect voltage control, you can call it, as we talk about indirect current control in case of D STATCOM. So, but in it support these self supported, because we are sensing the current and we are injecting the typically the voltage, most of the voltage at, you can call it in quadrature with the current, so that it does not need active power. So, a small amount of voltage is only injected for, you can call it in phase with the current which require active power. So, that self supporting DC bus is maintained like also. So, well, coming to the equation for this, these are the typically the component of PCC voltage in D and Q axis. So, we can call it the source voltage DC part, and this is for AC part, comes out from source side, because source side might have a power quality problem. So, you might have a AC as well as DC component for DQ, and the harmonics and oscillatory component in this are there, are eliminated by using low pass filter. In order to maintain the DC bus, a PI controller is used at DC bus of DVR, and the output is considered as the voltage loss for meeting its losses, and this is the PI controller which meets the losses. So, this is the DC link voltage error of DVR, and this is the PI controller one, and similarly for regulating the voltage for corresponding to reactive power. For regulation of voltage, we have a load voltage, reference load voltage, we have a reference load voltage amplitude, and we put the PI controller for that. That give you the typically the injection of voltage at 90 degree from the current, and corresponding reference we get from there. And from this we can find out direct and quadrature axis. So, here we from direct axis we take a loss minus, because that have to be taken from there, and quadrature axis we of course the corresponding to the what we want load and that to be injected, and 0 sequence is 0. And now we transform this VDVQ 0 to directly the load voltage, because these are the voltage across the load we require. So, we have instantaneous, sinusoidal, balance, regulated voltage, reference voltage, and we sense the load voltage, and we put the load on this load voltage pendulum current control. So, we call it, this is indirect voltage control across the load. So, error between the sense load voltage and the reference load voltage are used in the pendulum current control to generate the gating pulses of VSC of the voltage source converter of the dynamic voltage restorer.